Hello YouTube, I'm back from not uploading for a while. Today we'll be covering a practice final exam from Professor Reinsch from Berkeley Physics 105 course, which is classical mechanics. So today we're just going to solve problem 1, and we'll start off with part A. And you should have seen the problem at the beginning. I put an image up there at the beginning of the video. So what we have here for part A is two masses M1 and M2 connected by a spring, and our goal is just to find the Lagrangian. So part A is pretty straightforward. Lagrangian is simply kinetic energy T minus potential energy U. So let's see here. Kinetic energy. Well, mass 2 and mass 1 could be moving either direction. We don't know yet. So we'll describe the velocity at which M1 travels as x1 prime, and the velocity at which mass 2 travels is x2 prime. So the total kinetic energy is going to be T equals to 1/2 m x1 prime squared plus 1/2 m x2 prime squared. Now we know that from the beginning of the video you saw that m1 equals m2 equals m. So they all have the same mass value, which is why I didn't really need to put an M1 here or an M2, because they're all equal. So I'll just put M here. And then U, they gave us that value at the beginning of the video as well. It's 1/2 k xs squared, or 1/2 k x1 minus x2 minus L squared. So our Lagrangian in terms of x1, x2, x1 prime, x2 prime is 1/2 m x1 prime squared plus 1/2 m x2 prime squared minus 1/2 k x1 minus x2 minus L squared. So that's easy points. Okay. So now we're at part B, which was rewrite the Lagrangian in terms of x, the extension, or the relative distance between x1 and x2. Not the extension distance, but the distance between x1 and x2. And big X, which is the position of the center of mass. So we could begin by writing the Lagrangian formula, which is just T minus U. So we know that the total kinetic energy of the system is equal to the combined kinetic energy of this x position, this big X. It's with respect to big X and with respect to small x. So there's a formula that we need to know, and that is T equals 1/2 times big M, big X prime squared plus 1/2 mu x little x prime squared. So the formula is this, and M is equal to M1 plus M2, which we already know is 2M because we know M1 equals M2 equals M. And then the reduced mass, that's known as the reduced mass, which is something that we must use when we're dealing with the relative coordinates. So reduced mass is equal to M1 M2 over M1 plus M2. But since we know that they're all equal to M, little m, that's M squared over 2M, or 1/2 M. So, sorry, there's some smudging. So, with that being said, we can plug in our big M and our mu, reduced mass, and we'll have 1/2 times 2M big X prime squared plus 1/2 times 1/2 M little x prime squared. So that's equal to M big X prime squared plus 1/4 M little x prime squared. So we know that, but that's only 1/2 of the formula. So we now need to know what U is. So U is still 1/2 k xs squared, but we have to write it in terms of the relative coordinate x, which is x 1 minus x2. So we know that the only difference between xs and x is the L. So negative L. So we know that xs is equal to x minus L squared. So now we have everything in place to write the full Lagrangian. So our Lagrangian is going to be m big X prime squared plus 1/4 m little x prime squared minus 1/2 k x minus L squared. Sorry, it's getting in the way of other things. Okay, that's part B solved. Okay, so we are on the final stretch. So for part C, we have to solve for big X of t and little x of t given this Lagrangian. So we can start with the Euler-Lagrange equations and set up a system of equations since Lagrangian depends on two variables, little x and big X. So let's start. We know Lagrangian with respect to big X is equal to d dt Lagrangian of L. Derivative of Lagrangian with respect to x prime. And we know that the derivative of Lagrangian with respect to little l equals d dt Lagrangian of a derivative of Lagrangian with respect to little x prime. So we can solve for that. We know that the Lagrangian does not depend on big X at all, so we have 0. Since there's no terms with big X in it, then we can take the ddt of Lagrangian with partial of Lagrangian with respect to x prime. There is a term with x prime here, so we have ddt of 2m x prime, that's 2m x double prime. And then we can start at the second system of equations. So we have partial of L Lagrangian with respect to x. There is in fact a term with x in it, little x, so we have negative k x minus L using the chain and the power rule. So that's some calculus, I guess. And then ddt with respect to partial of Lagrangian with respect to x prime. There is an x prime, little x prime term here, so that's 1/2 m little x prime, or 1/2 m double little x prime. So we now have our solved system of equations, kind of. Now all we have to do is solve for big X prime and little x prime. So we know 2mx big X double prime is equal to 0. But we can cancel out 2m because they're constants and there's 0 on the other side. So we now just have big X double prime equals 0, where we know that big X double prime must equal at plus b, where a and b are both arbitrary constants. And then here we can solve for this differential equations, where we have 1/2 m little x double prime plus k times x minus L. I just rewrote it. I just rewrote it in a slightly different way. So then this is equal to 1/2 m x double prime plus kx equals kl. So here we know that there must be an L as a constant added onto whatever we get because of the L here. Plugging in L will get us KL, and then it will get canceled out in the second derivative, so L can be there. And then here we have to solve for the homogeneous equation. So let's do that. So 1/2 m little x double prime plus kx, pretend that it's 0 here. Then we know that we can just divide everything by 1/2 m. So we will get x double prime plus 2k over m x equals 0. And then this is equal to r squared over 2k over m equals 0. So we know r is equal to 0 plus or minus square root of 2k over m I. So with that being said, using the techniques that we learned from one of my past from my past ordinary differential equations videos, we know that because r is 0 plus or minus square root of 2k over m times the imaginary number, we get c1 cosine of square root 2k over m t plus c2 sine, wait, let me erase that, 2k over m t. Okay, so we now know that, oh wait, shoot, why did I put double prime? We now know that big X equals AT plus B, and little x is equal to L plus C1 cosine square root 2k over m. I'm not going to read the rest of it, you can read it yourself. Where C1, C2, A, and B are arbitrary constants that we don't know since the problem did not give any initial conditions. So, describe the motion. Well, we know that the center of mass, which we'll just mark here, it depends linearly and just moves in one direction. It doesn't oscillate or waver, just goes in this direction or goes in this direction at a constant speed. So about this one, we know that the change or the distance between x or x1 and x2, it kind of wavers a little bit, but it always kind of stays positive because L is a positive number, never strays complete or too far. And I don't know what to say, it kind of just oscillates, wavers a little bit because of the cosine and sine